Today we're doing lesson 11.4, limits at infinity and limits of sequences. This lesson has a lot of overlap with rational expressions, and you'll see that spread throughout some of the theorem slides we go through today. Definition of limits at infinity, right? The definition of limits at infinity is if f is a function and L sub 1 and L sub 2 are real numbers, then the statements limit as x goes to negative infinity of f of x equals L sub 1 would be a way to write the limit as x approaches negative infinity, and similarly limit as x goes to infinity of f of x equals L sub 2 would be how we would write the limit as x approaches positive infinity. Now these denote the limit at infinity. The first statement is read as I already did, and then down here limits at infinity, if r is a positive real number, then the limit as x goes to infinity of 1 over x to the r equals 0, right? Basically like rational functions, right? Remember, if we had 1 over x, that meant our graph, after we simplified, that meant our graph as we went to the right would go to 0, or to the left would go to 0. So notice, they write it 2 times, but it's the same, whether it's plus infinity or minus infinity. The limit of 1 over x to any positive exponent, even 1 over x, would say that we are going to y equals 0, right? That's what that is saying. And again, negative infinity is talking about limits to the left of the graph, positive infinity, limit to the right of the graph, but we're not doing any graphing today, just talking about the differences. So find the limit. Limit as x goes to infinity of 7 plus 4 over x squared. So what we're going to do is we're going to split it up, right? This is the same as the limit as x goes to infinity of 7 plus the limit as x goes to infinity of this piece. So splitting it up, well, limit as x goes to infinity of 7 is 7. The limit as x goes to infinity of 4 over x squared, well, we have a number of x in the denominator. This means this piece is going to go to 0, right? 4 over 100 squared is almost 0, and so on. So 7 plus 0, right? We simplified each piece, gives us the limit is 7. Okay, right? This doesn't have an x, so that's why this limit is 7 for the left part. This is 0 from the definition we just did, and then we're adding or subtracting. Next one we're subtracting here. Limit as x goes to negative infinity of 5 minus 11 over x to the 5th. Splitting it up again, one piece at a time. Limit as x goes to negative infinity of 5. Well, that's 5. Limit as x goes to negative infinity of 11 over x to the 5th. Well, x, the denominator wins, I believe is how I said it before, right? Larger degree, and so that would be 0. So 5 minus 0, right? The minus sign comes down, gives us positive 5. Next, the next rule here is limits at infinity more thoroughly explained, right? Consider rational function n of x over d of x, where n is a sub n of x to the n, dot, 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 and d of x is b of sub n of x to the n, dot, dot, dot. Right, so this is the highest piece, the leading coefficient, the degree, and so on, right? Just like graphs of rational function, okay? Limit of f of x as x approaches positive or negative infinity, right? Either infinity is, we go to 0 if our numerator is less than the denominator's degree. Now, I don't like the m, so I always wrote it like this. N less than d. Now, we are equal to leading coefficient of the numerator over leading coefficient of the denominator if our degrees are equal, right? When n equals d, leading coefficient. And if the numerator is greater, then the limit doesn't exist because we aren't approaching a value, continuing to increase, and so on, right? So very similar. Now, in general, how I deal with these problems are, I'll look at this piece. For example, find the limit as x goes to infinity of 5x fourth plus 4x squared minus 5 over 8x squared minus 7x to the fourth plus 10. And I will we'll pick a shape here. And what I'll do is I'll just box the terms that are important. 5x to the fourth is a big one. Bottom one, minus 7x to the fourth. And then I'm just going to rewrite just those terms. And then I'm going to cancel anything they have in common. X to the fourth cancels top and bottom. And then I'm bringing the limit back. So 5 over negative 7. And we're taking the limit of that as x goes to infinity. Well, there's no x's left, so our limit is negative 5/7. Same thing over here. We've got 5x to the fourth plus 3x cubed, so on. Numerator over denominator as x approaches negative infinity. Okay, the top one looks standard form, bottom one looks standard form, so we're just kind of looking at those two pieces. 5x to the fourth over x to the fifth. Well, 4 of the x's will cancel, and we'll still have 5 over x left over. So this is like 1 over x. We've got a positive degree in the denominator. Denominator wins. We're going to go to 0. A couple more of these. Limit as x goes to negative infinity of 6x squared plus 4x plus 1 over x and 6. Go ahead and try those on your own. And our answers. Left side does not exist. Right side is 1/3. Walking through, again, 6x squared over x. This leaves us with 6x. Well, as x gets larger, numerator clearly 1. We don't even have a denominator, so it does not exist. Over here, 7x cubed over 21x cubed. The x cubes cancel. 7 over 21 is 1/3. And there's our answer, 1/3. Continuing. One more set. You can try it on your own since we've done this before. And unveiling, 12x fourth over 2x to the fourth. The x fourth cancels. 12 over 2 is 6. So our answer is 6. X squared over x cubed. Denominator wins. We're going to go to 0. In comparison, it'd be the same as 1 over x, which is 0. Finishing up here, we've got one last part. The limit of a sequence. Let L be a real number and let f be a function of a real variable such that the limit as x goes to infinity of f of x equals L. If a sub n is a sequence such that f of n equals a sub n, right? So we can basically write the function as the sequence, then the limit of that sequence is L. So basically, if it's in kind of the same pattern we were just seeing, we can actually have a converging limit versus a diverging. Like we're going to converge to a value, right? So converging means as n increases, the terms of a sequence get closer to a number, right? So we converge to a point or a number. Diverge, like divergent, we do not get closer to a number, right? It just keeps getting larger and larger. So starting off here, we've got the limit of a sequence, 8 over n cubed times the quantity n times n plus 1 times quantity 2n plus 1 all over 6. Now, you could technically do this algebraically, but I did this with the table, so I just plug things in on the calculator, and I've got 3.08. For 10, 10 squared or 100, 2.7068, 1,000, 2.67, 10,000, 2.667, 100,000, 2.6667. So this looks to be approaching 2.6 repeating, right? Weren't close here, getting closer. Now to 1 digit, 1 decimal, 3 digits, 2 decimals, almost 4, right? Almost 4 decimals. So it is 2.66 repeating, like 2.6 repeating, or that is the same as 8/3. Now algebraically, right, we could just look at, well, what would have the leading term? Well, 2n times n times n times 8, right? Because each n, that's going to be our largest term. So n times n squared, times 2, 2n cubed, times 8 gives me 16n cubed. Bottom one is just 6n cubed, right? So just doing that math, because the bottom only had one piece, but looking up, n cubes would cancel. 16 over 6 is 8/3, which would equal that 2.66 or 2.6 repeating I was talking about. And that would be the limit. That wraps up today's lesson. Well, definitely let me know by email if you have any questions. Thanks.